we have a box here. It's held in a static equilibrium. At point A, it's connected. It's connected to a rope. That rope is connected to a ring at point A. The ring at point A is held by three, I would say, cables: cable AD, cable AB, and cable AC. Now, I'm asked to find the force in each cable. And what I know is that this mass here is 40 pounds. So this is 40 pounds. Let me just briefly write down. So what you're asked to do is to determine the force in each cable used to support, I think, the 40 pounds box. 40 pounds box. These are very interesting, as simple as they are or basic as they look. Later on in your career, you're going to do this over and over when you even design different structures and different things in engineering. And as simple as they are, very practical, pretty much always later on when you design different objects. So very simple but very powerful process. So that's why Newton's laws are just beautiful. So where do I start? This time, before I even get to details, this time we are not given any information about angles that these cables are creating with different axes. Right? I'm told that this is X axis, this is Y axis, and this is Z axis. Right? They already gave me the axes. But no information about what angles these cables are forming with these axes. So, but one thing I do have is I can find the coordinate of each point. If well, as I said first, we are going to go with the free body diagram for the point we have the most information about. These problems are pretty straightforward because I guess by just looking at it, first thing comes to your mind is that, well, I'm just going to isolate this point and draw the free body diagram for point A. And that's pretty much what I'm going to do. Let's first do that. So small steps, step by step. I actually don't remember. Did I draw free body diagram to be consistent with what you were doing with green? So, not that it matters, but I just want to make sure that we are relatively consistent with coloring. So let me raise that. So we're going to draw it with green, following the same approach. So I'm going to draw X here. I just want to draw the free body diagram. Let's say draw X axis here. I'm going to try to follow the same parallel to what we have there. And this is Z. So name them. This is X, this is Y, and this is Z. This is point A. Now, let's start with the forces. All right. The first one is, I'm going to go with the obvious one. The box is 40 pounds downward, so it's pretty much this way. And I put it there, 40 pounds. And I have 3 cables. All right. Cables can only be in tension, so I'll just put those forces here. I'll put one here along AD. Another one here, I try to make it 3-dimensional, and another one here. These are just cables, so TAD, right? TAB, and TAC. Oh, good. Now we have a free body diagram. Hopefully there is no confusion about this part. The problem is, how am I going to form Newton's second law, summation or vector sum of all the forces is equal to 0. How do I form that equation? And say, well, along x and y and z, I can write that equation and then find the force values in these cables. How do I do that one? How can I decompose these force vectors along these axes? I don't have the angles. I do know one thing. I want to express force vectors in Cartesian space. That's what I always do. Previously, in previous example, I had the angles, so I could use those angles, sine and cosine, and express the force or force vectors in Cartesian space. Now, to do it here, I have to use what we talked about in the previous class about force vector, finding a force vector along a specific line. Remember, I said if we have 2 points in one line, we can find the unit vector along that line and multiply the magnitude of force to that unit vector by that unit vector. So we can find the force along that vector or along that line, passing through those 2 points. Now, what I'm trying to say is that, well, let's see what points do we have. We're looking for TAB, TAC, and TAD, right? Components in different directions for these 3 forces. Now, if I have this point A, let's say I want to start with TAB. If I want to start with TAB, I need to know the coordinates for point A and point B, so I can form the unit vector and use that unit vector to find the components of force along this direction. Right. So if point A, what is the coordinate of point A? Can someone tell me in X, Y, Z coordinate system that we have?
0, 0, 0.
0, 0, 0, exactly, because it's pretty much is the origin. How about point B? What is the coordinate of point B now? That's a little more challenging. Look at the values. What is the X?
3.
4
and
minus 3. Because X
Negative
positive
3,
direction
okay.
is this way, right? So it's minus 3. What is Y?
-4.
Y is -4, exactly. And Z is just 8 going up. Right? Hopefully you see that. So I'm gonna -4, yes. Yes, Richard, that's pretty accurate. -3, -4, 8. I'm a little delayed looking at chat box, but thank you guys. So now I have the coordinates. Remember, how did I do? If you take a look at your notes, you will see I pretty much I formed the unit vector from A to B by subtracting each components of each point from the other point. I'm trying to say that, well, this one was XB, YB, ZB, and this is XA, YA, ZA. So I said the unit vector is pretty much R, or the vector, before even getting to unit vector, is XB minus XA. So this was minus 3I. This would be minus 4J, because it's YB minus YI. And ZB minus ZA, which is plus 8K. So this is my vector from A to B. This is RAB. I'll just call it A, but we can call it RAB. Now to make the unit vector, we just divide this by the magnitude. And magnitude is the square root of the squared of each element in this vector. Now I'm just gonna write everything at the same time. So I'll say I want TAB, force along AB, is the magnitude of TAB, whatever it is, which we don't know, we want to find, multiplied by the unit vector formed by RAB, or unit vector along RAB. And that would be minus 3I minus 4J plus 8k divided by the magnitude of RAB, which is minus 3 squared plus minus 4 squared plus 8 squared. So this gives me TAB magnitude, whatever it is, multiplied by. If I divide minus 3 by whatever is the value of this, the denominator is, I'll get the first component of unit vector. It's minus 0.318. Divide minus 4 by that magnitude, you'll get the second component of the unit vector is minus 0.424j. And the last one would be 0.848, this is 8k. So now I have the Cartesian representation of vector AB. Good, now I know the components in each direction. I don't know the magnitude yet, TAB, that's what I'm trying to find, but I know the exact direction in this space. Now I'll do the same thing for AC. What is point C? Coordinates of point C. If you look at point C here, I want to find this vector now, RAC. If it starts from A, well, A is there. What is the X value?
It's -3, positive
negative-
4, and then
-3, 4 and 8, right? Now this would be XC, YC, ZC. So the unit vector RAC would be whatever is the X of C minus X of A. We're going from A to C. So corresponding components should be subtracted. XC minus XA would be minus 3I. YC minus YA would be plus 4J. And 8 minus 0 plus 8k. Now this is the vector R passing point A and C. Now I can find, so following the same process, TAC would be the magnitude of TAC, which I don't know what it is, multiplied by, I'm going to find the unit vector for AC. So minus 3I plus 4J plus 8k divided by square root of minus 3 squared plus 4 squared plus 8 squared. If you do this math, TAC, which I don't know the magnitude, I can write it better, TAC. TAC times unit vector. So the values for that unit vector would be minus 0.318I, correctly, yeah, plus 0.424J. Sorry for the mess. I'm going to write a K value here, which is pretty much the same thing as before, previous one, K. So now this is the vector representation of AC in Cartesian space. Good. Now I have AB and I have AC. What about AD? What is AD? I don't have the coordinate of point D. How do I find TAD? Well, I know its magnitude should be multiplied by some vector. Look at the figure here, right? From A to D. Right? This is what I'm looking for. What is this direction?
Is it 300?
It's pretty much 300, and what you get is pretty much I. Right? Whatever is the magnitude in I direction. And the last one would be W, or weight. I can just call it W here. How about that? Well, I know its magnitude is 40. What is the vector representing that? So this is z-axis. And this is downward. So what would be the vector represent? Minus k, yes. So that would be minus k pounds. So I got TAB here. Right, that's not just number now. TAB, TAC, TAD, and W. So now I have all the forces in my free body diagram represented in Cartesian space. Now, I don't know 3 magnitudes there, but keep in mind, I'm going to get 3 equations, right? If you think about it, I'm going to write this in X and Y and Z direction. So I'm going to get 3 equations. So having 3 unknowns is not a big deal because mathematically speaking, I should be able to solve it. So let's do that. I'm going to write the equation of motion. Well, not the equation of motion exactly. Newton's first law, and say the summation of forces is equal to 0 or to 0. Now it can be written in each direction. So in X direction is 0. Summation of forces in Y direction should be 0. Summation of forces in Z direction should be 0. We are in a static equilibrium. Now let's do that. Now in X direction, summation of forces in X direction is 0. This gives me, if you go back there, what I'm going to write now is summation of forces in each direction, right? I'm going to write, let me see if I can do it. TAB minus this, minus 0.318 TAB, minus 0.318 TAC, which is components in X direction, and TADI. These are only, I'm looking at components with I, right? Because I'm just writing the values in X direction. That's pretty much it. W is in K direction and doesn't come to this equation. So I'll get minus 318 T, I believe was AB, make sure, minus, oh, this should be minus. Minus 318 T was AC plus TAD is equal to 0. This is equation 1. Summation of forces in Y direction. Going back. I'm going to come back to this page. These values. So let me use a different color. So that would be TAB multiplied by minus 0.424, TAC multiplied by plus 0.424, and that's pretty much it. I don't have anything on TAD. That vector has no J component. W has no J component. So if I write the equations in that direction, it gives me minus 0.424 TAB plus 0.424 TAC is equal to 0. From here, immediately you can see TAB and TAC are equal. This is the second equation. Last, not the least, in Z direction. Just put them all together. Go back, same process. Looking at this, this is the Z direction component from vector AB is going to be 0.848 TAB, 0.84, this should be point. I'm going to be tricked. Okay, let me be a little more diligent and actually put also 0 there. This should be point. And the unit vector has the magnitude of 1, can't have 800 as one of the components. So 0.848 TAC, and W also now has a component in Z direction. Nothing comes out of TAD. So I'll go back there and I put all of these together. 0.848 TAB plus 0.848 T AC minus 40 is equal to 0. That would be your third equation. So mathematically speaking, we have three equations, three unknowns. All right, we should be able to solve this. The easier way, if you want to actually do it manually, we can just use this TAB is equal to TAC, plug it back to equation number 2. So from there, you can actually find TAB or TAC, if I'm not wrong. TAB is equal to TAC, plug it there. There you go. You get that one. And once you get TAC, TAB is equal to TAC, you can go to equation 1 and find TAD. The other way is just TAB is equal to TAC. You can put TAB and you can replace TAB or TAC in the first equation. Then equation 1 and 3 gives you two equations, two unknowns, and we can solve that. Right? Whether either way, you can just go about this. So if you do that, I'll just give you the answer. TAD becomes 15 pounds and TAB becomes 23.5, I guess I went another one, 0.58 pounds. You don't really need to do that. And since TAB and TAC are equal, so obviously TAC also becomes 23.58 pounds. So there you go, that's what we were looking for. The value of force, I'm gonna come back. Determine the force in each cable used to support the 40 pounds box. We found the force in each cable.